Section: Introduction. We're going to talk about how we've been working on improving the training of transformer models. These models have been making great strides in areas like chatbots and image generation, but the training process isn't always smooth sailing. Sometimes, the training can become unstable, which can slow down or even disrupt the learning process. As we continue to scale up these models, it's crucial to understand why these failures occur and how we can prevent them. In our study, we've been able to reproduce and predict these instabilities. We've found that by examining the relationship between the learning rate and loss across different scales, we can identify when instability is likely to occur. To help with this, we've introduced a concept called learning rate sensitivity. This measures how much the performance deviates from the optimal when we change the learning rate. Interestingly, we've found that two sources of instability, which have been previously identified in large-scale models, can also occur in smaller transformers. This is great news because it means we can study these instabilities without needing a lot of resources. Specifically, we've been looking at the growth of logits in attention layers and the divergence of the output logits from the log probabilities. Both of these instabilities tend to occur at high learning rates in smaller models. We've also found that certain interventions, such as QK layer norm and Z-loss regularization, can reduce learning rate sensitivity and help ensure successful training across a wide range of learning rates. This has led us to question how other known optimizer and model interventions might affect the learning rate versus loss curves across different scales. We've studied the effect of techniques like warm-up, weight decay, and mu-param in this context. When we use QK layer norm and Z-loss regularization, these other techniques don't usually affect the range of learning rates at which models can be stably trained, but they do affect the sensitivity to learning rate within this range. One interesting discovery we've made is that increasing the depth of a model increases learning rate sensitivity more than increasing the width. We've also found that we can predict an instability before it happens by looking at model characteristics like activation and gradient norms. Our research has also shown that gradient norms decrease with both scale and learning rate, which means that the default atom W epsilon hyperparameter is too large and causes updates that are too small. We've linked this phenomenon and the attention logit growth instability to parameter norm growth. In conclusion, our work opens up new opportunities for studying training stability without needing a lot of resources. In terms of our experimental methodology, we've been training small transformer models using a similar setup to GPT-2. We've been using atom W with specific default values for beta_1, beta_2, epsilon, and gradient clipping. We've also been using a linear schedule for warm-up and a cosine decay schedule for the remainder, with a minimum learning rate. We've been using pre-normalization transformers with QK layer norm and no biases. We've been scaling up the embedding size, depth, and number of heads when scaling parameters. We've been using rotary positional embeddings and training data from C4. The feed-forward component of the transformer is an MLP with a hidden dimension of 4 times the model dimension and JLU activations. We've been initializing the embedding with a normal distribution and the rest of the weights with a truncated normal distribution. Finally, we've been using a batch size of 256, with each batch element having a sequence length of 512 tokens. We've been training on TPUs in B-float 16 precision using FLAX and JAX. Section Summary. Scaling up transformers has led to significant advancements in various domains, but training large models can be unstable and hinder learning. In this report, we reproduce and study training instabilities in transformer models, particularly focusing on the relationship between learning rate and loss. We find that measuring learning rate sensitivity, which quantifies the deviation from optimal performance when varying learning rate, is a useful tool for identifying instability. Section: LR versus loss curves and learning rate sensitivity. We're going to delve into the relationship between learning rate, LR, and loss in models of varying sizes to understand how instability in models arises with scale. A common sign of instability is a sudden surge in loss when the learning rate is high. By plotting LR against loss, we can see how the lowest unstable learning rate changes with the size of the model. To summarize these plots, we use a measure called LR sensitivity. This measures how much the final validation loss deviates from the optimal loss when the learning rate is varied across a wide range. If a model can't handle high learning rates and fails to train, its LR sensitivity will be high. However, there are situations where these plots and LR sensitivity may not be useful. For example, if an intervention changes the meaning of the learning rate. Let's define some terms. Suppose we have a model with weights, which we'll call theta, that we obtain when we train with a certain learning rate, which we'll call eta. The validation loss when using these weights is denoted as L, theta. If we have a range of learning rates from A to B, the loss obtained with the best learning rate in this range is denoted as L. In other words, L is the minimum loss we can get when we vary the learning rate between A and B. LR sensitivity is then defined as the average difference between the loss obtained with each learning rate in the range and the best possible loss, L. Unless stated otherwise, we use a learning rate range from 0.0003 to 0.3 with the Atom W optimizer to measure LR sensitivity. The learning rate refers to the highest value in a cosine decay schedule with warm-up. We consider learning rates of 0.0003, 0.001, 0.003, 0.01, 0.03, 0.1, and 0.3 when calculating the minimum and average. We also find it useful to look at how model characteristics like gradient or activation norms scale to predict instabilities. This is a different approach from previous work, which mainly focused on trends relating model scale and loss. In the following sections, we present our findings on training stability for small transformers. We use LR sensitivity to study two known instabilities and how to mitigate them at a small scale. We also explore how other model and optimizer interventions affect the sensitivity of the final loss to the learning rate. Lastly, we try to predict when instabilities might occur before they actually do. We start by reproducing two known instabilities at a small scale: the growth of logits in attention layers and the divergence of the output logits from the log probabilities. We show that these instabilities can be reproduced in small models by using high learning rates and that the mitigations used at larger scales are also effective here. One issue that has been documented before is that transformer training fails when the attention logits become too large. This was observed when training a vision transformer model with 22 billion parameters. In the self-attention layer of a transformer, queries and keys are combined to compute the attention logits, which are then passed through a softmax function to produce attention weights. These weights are used to combine values. When the attention logits become too large, the attention weights collapse to one-hot vectors. To solve this problem, a method called QK layer norm was proposed, which applies layer normalization to the queries and keys before computing the attention logits. Our experiments show that even small models can exhibit instability related to attention logit growth. Using QK layer norm increases the maximum learning rate at which small models can be trained. Without QK layer norm, the learning rate at which models diverge decreases as the model size increases. However, models with QK layer norm show significantly lower LR sensitivity and can be trained to low loss at high learning rates. Interestingly, QK layer norm allows training a model with 1.2 billion parameters at a learning rate of 0.3. Both with and without QK layer norm, LR sensitivity increases with scale. Our results suggest that attention logit growth is due to growth in the queries and keys, not due to an increase in their alignment. We also connect this instability to the quadratic dependence of attention logits on parameter norms. Section summary. LR versus loss curves and LR sensitivity are useful tools for studying model instability and the relationship between learning rate and loss for models of different sizes. LR sensitivity measures the deviation in final validation loss from optimal when sweeping LR across a range, and high LR sensitivity indicates a model's failure to train at high learning rates. By examining LR versus loss curves, the attention logit growth instability in transformer models can be reproduced in small models using high learning rates, and the mitigation technique of QK layer norm is effective in reducing LR sensitivity and allowing training at high learning rates. Section. Output logit divergence. We've noticed that when training large models, there can be a divergence in the output logits from the log probabilities. This divergence is a type of instability that we've been able to reproduce with smaller models at high learning rates. However, we found a way to mitigate this issue. To explain this in simpler terms, let's say that y represents the model's output logits. These logits are used to calculate class probabilities, p_i, through a softmax function. The softmax function is calculated as p_i equals e caret y_i, z, where z is the sum of e caret y_j for all j. This instability happens when the logits diverge and become very negative. We've observed this in a model with 2.4 million parameters at a learning rate of 0.1. Unlike the attention logit growth instability, this divergence happens towards the end of training. To mitigate this, we propose to keep log z close to 0. We add an auxiliary loss, log squared z, also known as z loss, with a coefficient of 0.0001. We've found that this instability related to output logit divergence happens in models without weight decay, regardless of their size, and z loss resolves this instability. Weight decay also mitigates this instability for the larger models we test. We've also looked at how other known model and optimizer interventions affect the shape of learning rate versus loss curves across scales. We've examined techniques such as warm-up, weight decay, and the mu parameter. For instance, a longer warm-up period reduces learning rate sensitivity, especially for larger models. We've also found that parameterizing weight decay independently of learning rate reduces learning rate sensitivity. We've also observed that increasing the number of parameters increases learning rate sensitivity. We've found that scaling depth increases learning rate sensitivity at a faster rate than scaling width. However, at the largest scale we test, independently scaling depth produces a model with lower validation loss. We've also tested the effect of the mu parameter on learning rate sensitivity. While the mu parameter does stabilize the optimal learning rate at the scale we test, it does not improve loss or reduce learning rate sensitivity in our experiments. In conclusion, we've found that mitigating output logit divergence and adjusting learning rate sensitivity can improve the stability of large models. We've also found that scaling depth can produce a model with lower validation loss at the largest scale we test. Section Summary. Researchers have identified two instabilities in training large models: divergence in the output logits and sensitivity to learning rate. The proposed mitigation for the output logit divergence is to encourage the log of the class probabilities to remain close to 0 by adding an auxiliary loss. Additionally, the study explores the effects of common techniques such as warm-up, weight decay, and independent weight decay on the sensitivity of learning rate, and finds that scaling depth increases LR sensitivity at a faster rate than scaling width. The $mu$param method stabilizes the optimal learning rate when scaling model width but does not improve loss or reduce LR sensitivity. Section: Additional Interventions. In this section, we're going to explore the effects of additional interventions or changes in hyperparameters on our model. We'll be referring to some figures in the appendix to help illustrate our points. Firstly, we found that altering the number of training steps, whether increasing from 100,000 to 200,000 or decreasing to 50,000, didn't significantly affect the model's sensitivity to learning rate. We also experimented with applying QK layer norm across the entire model dimension, rather than on a per-head basis with shared parameters. The results showed that the latter approach performed better, so we decided to use per-head QK layer norm as the standard in all other experiments. We also discovered that increasing the batch size from 256 to 512 or 1024 didn't significantly affect the model's sensitivity to learning rate. To keep the amount of data constant, we reduced the number of training steps when we increased the batch size. We believe that even if we kept the number of steps constant, the result would be the same, as changing the number of steps didn't affect learning rate sensitivity when the batch size was 256. We also looked at the effect of changing the weight decay from 0.0001. We found that increasing decay slightly shifted the optimal learning rate to the right. We also discovered that the instability in the growth of the logit was not due to the softmax in the self-attention layer, as it still occurred with a pointwise variant of attention. A key question we wanted to answer was whether we could predict these instabilities. We tracked the maximum attention logit across model scales and fitted a curve to the data. Using this, we predicted that a model with 4.8 billion parameters would be unstable at a learning rate of 0.01 without QK layer norm. We ran an experiment to confirm this prediction and found that our model did indeed diverge as predicted. We also noticed that all points with attention logits above 10,000 diverged. Moreover, our quadratic fit predicted that the next model scale would also cross this value for a learning rate of 0.01. Based on this prediction, we trained a new model with 4.8 billion parameters at a learning rate of 0.01. This model also diverged as predicted. We then asked whether we could have predicted that instability arises when the max attention logit exceeds 10,000 without manipulating learning rate and model size. We took initial steps towards an answer by transplanting different values of max attention logit into a small network with 10 million parameters. We found that loss deteriorated around a constant of 1,000, and by a constant of 10,000, the loss exceeded that of a zero-layer bigram model consisting of the transformer we use without any self-attention or MLP layers. In the next section, we examined whether the scaling behavior of model characteristics can be used to predict new issues with the default model and hyperparameter settings. We found that as models get larger, the value that gradient root mean square, RMS, approaches is cause for concern. At the largest scale and learning rate we tested, gradient RMS was around the default atom W epsilon hyperparameter. If the gradient RMS is on the same order as epsilon, then the update will decrease in magnitude, and parameters will not receive learning signals as intended. To mitigate this issue, we simply lowered the atom W epsilon hyperparameter from its default of 1E8. We conducted this experiment for a 4.8 billion parameter model at a learning rate of 0.3 and found that decreasing epsilon to 1E15 improved loss and mitigated a collapse in gradient RMS. We believe this improvement will only increase at scale. On the other hand, increasing epsilon to 1E6 resulted in an instability. We also found that for larger networks and learning rates, the transformer output RMS entering the final layer norm will grow. Since the layer norm gradients are scaled by the inverse of their input RMS, the gradient received by the transformer will shrink. For a more detailed discussion, please refer to the appendix. Section Summary. In this section, the authors explore additional interventions and hyperparameter changes to understand their impact on the logit growth instability in self-attention models. They find that changing the number of training steps or increasing the batch size does not significantly affect the instability. They also investigate the possibility of predicting the instability before it occurs and demonstrate that it is possible to predict the logit growth instability based on the scaling behavior of model characteristics. Additionally, they identify a new issue related to the gradient RMS and propose lowering the atom W epsilon hyperparameter as a mitigation strategy. Section: Related work. In this section, we'll discuss the related work that has influenced our research. Our study primarily focuses on the impact of known interventions and instabilities. We've drawn from previous research where relevant, such as the attention growth instability observed by certain researchers, and the final logit divergence issue encountered by others. We've also taken note of similar experimental methods used in previous studies. For example, some researchers have also examined the relationship between learning rate, LR, and loss across different scales. However, their focus was on centering the optimum. Other researchers have induced instability in base models by doubling the learning rate and measured the presence of outlier features as a function of scale. There are also significant instabilities and related topics that we haven't directly discussed yet. For instance, we've mainly focused on instabilities that lead to a slow divergence, but there's also research on fast loss spikes. This type of instability is characterized by a rapid increase in the loss that often eventually recovers. The traditional understanding of gradient descent suggests that loss instability only happens when the learning rate exceeds twice the maximum eigenvalue of the Hessian matrix. However, recent studies into large batch neural network training dynamics have revealed a more complex picture. When training neural networks with large batch stochastic gradient descent, SGD, the loss curvature constantly changes due to the interaction of two processes, progressive sharpening and self-stabilization. Progressive sharpening is the empirical observation that when the learning rate is less than twice the maximum eigenvalue of the Hessian, the curvature gradually increases until the stability threshold is violated. When the learning rate becomes too large relative to the curvature, fast loss spikes occur and the parameters oscillate into a region with a smaller maximum eigenvalue of the Hessian, where stable training and progressive sharpening resonates. The process where instability results in a smaller maximum eigenvalue of the Hessian is called self-stabilization. A theoretical model of this process has been provided in previous research. It was shown that gradually reducing the maximum eigenvalue of the Hessian via self-stabilization is a primary mechanism behind the success of learning rate warm-up. Other researchers have further analyzed the edge of stability of dynamics with adaptive optimizers, showing that progressive sharpening interacts with both the self-stabilization process and the adaptive optimizer state. This interaction results in the preconditioned sharpness oscillating around an optimizer-specific threshold. Adaptive edge of stability, AEOS, can also result in periodic loss spikes when progressive sharpening pushes the preconditioned sharpness above the stability threshold. However, the optimizer hyperparameters play a role. In particular, when the learning rate is greater than a certain value, two mechanisms are now in play to resolve the step size being too big. Either the Hessian can shrink or the preconditioned Hessian can shrink, or both. It was found that when a certain parameter is large, the Hessian tends to shrink and fast loss spikes result during the process, resembling the self-stabilization process observed with gradient descent. However, when this parameter is small, the preconditioned Hessian tends to shrink, no loss spikes are observed, and the maximum eigenvalue of the Hessian tends to gradually increase throughout training. It's worth noting that the adaptive edge of stability process studied in previous research offers a more complete understanding for loss spikes. For example, it's argued that during training of transformers with adaptive optimizers, the optimizer update can become too big, resulting in a loss spike followed by recovery. This is sometimes attributed to the adaptive optimizer state becoming stale, which is consistent with the observation that reducing a certain parameter resolves the loss spikes. AEOS also offers an explanation for the periodic loss spikes observed when training large transformer models. While our work has studied sensitivity to learning rate, there is also research that aims to eliminate the need to specify a learning rate. Based on their analysis, some researchers set the step size for iteration to the maximum distance from the initialization divided by the root sum of historical gradient squares. Moreover, while our work investigated a certain parameter, there are additional parametrizations for which it would be interesting to explore the relationship between learning rate and loss.